according to you. So, I read your papers are poetic, I would say.
Oh,
So now we are looking forward to your lecture. Over to Professor Ono.
okay. Thank you. Thank you very much, Professor Nair and Professor Bhargava. I regret that we can't be together in person. I think I've met many of you on some of my earlier trips to India, but this is the era of COVID, so we make best do with what is available to us, and thankfully Zoom exists. And so good evening to you, and here in the United States it is early morning, so what better reason to wake up early than to celebrate Ramanujan's birthday and your National Day of Mathematics. So let me begin by sharing my screen, and in fact, before I give my talk, I want to share this photograph. It's one of my cherished photographs. I am much younger than, maybe 10 years ago, but I think most of you can recognize almost everything about this photo. This photo was taken in Kumbakonam in front of Ramanujan's childhood home. And with me was my late good friend, Dick Askey, who was one of the most important and influential experts in the theory of special functions. And I had the great pleasure of taking a trip to India with him. I think the same year I met you, Professor Bhargava, in Mysore.
Right,
Yeah,
right.
this was that year.
Yeah, both of you were in Mysore, 2012.
I think so. I think this was the year that Dick and I traveled around India, and it was a very special occasion.
Yeah,
And given that I'm
we were very lucky to have Professor Askey in Mysore.
yes,
And I was
so
his guest also in Madison long ago.
okay.
I stayed in
So
his
Dick
house,
was
had the hospitality of he and his wife.
yes. So Dick was very important to me. He helped me get a position at the University of Wisconsin, where I was a professor for many years. To this audience, he must be a hero. This is the community of special functions experts. But on top of all of that, Dick is very important today on December 22nd, Ramanujan's birthday, because he is very important for helping make Ramanujan a household name, at least in North America. You see, he led the fundraising campaign where mathematicians around the world contributed to the commissioning of the very famous Ramanujan bust. And my father was one of those mathematicians who contributed to this. And, one of my prized possessions is a letter that Janaki Amal sent my father, thanking her for being part of Dick's major effort. It's in my wall on my wall in my office at University of Virginia, and it sort of marks the beginning of my mathematical life. And so I know you want to hear me give a talk about AGM and maybe jellyfish, but I do think it's very important to begin this day remembering not only Ramanujan, but also people like Dick, who have played a very important role in making sure that Ramanujan's mathematics has reached a broader community. And for all of these reasons, I think we should begin this conference, or at least I begin my talk by acknowledging these two very great men. Okay, so let me begin my talk. I have not yet ever given this talk, so I might be a little bit discombobulated in my presentation, but I shall do my best. All right. I wrote this talk a few weeks ago with this conference in mind, largely because I think that special functions, although I'm not an expert in special functions, I think that special functions are ubiquitous. I think they are all over mathematics. And part of my talk today is to bring together some themes involving special functions, which perhaps have not yet been connected before. So I'm going to talk about the arithmetic and geometric mean, which is very closely related to special functions, as I think this audience knows very well. Somehow I'm going to bring in the idea of jellyfish, and I'm going to tie that all together with some number theory, elliptic curves. And so on this slide, you can see three pictures. On the left, you have an image of the AGM. In the middle, there's some creatures, jellyfish. And on the right, there's a bizarre geometric pattern, which is assembled from graphs of an elliptic curve. So this lecture is based on a paper I've written with my former student, Michael Griffin, and two of my current postdocs, Neelam Sakia and Waylun Sai. Neelam is actually from India. She's enjoying her time here at the University of Virginia enjoying a Nehru Fulbright scholar. And I think her plan is to return to India sometime in 2022. So I hope you get the opportunity to meet with her and invite her into your community as she is quite young and quite vibrant and exciting. So let's get to the math. The arithmetic and geometric means, we learn about some of the theory of the arithmetic and geometric means in grade school. So in grade school, when you're a young child, you learn about averages. And the arithmetic mean, as you see here, of two positive real numbers, A and B, is just A plus B over 2, the average. We don't always use the language geometric mean, but at moment's glance, you know what we mean. The geometric mean is the square root of the product of two numbers, A and B. In both senses, they are averages, one in an additive sense and one in a multiplicative sense. And at first glance, there should be no relationship between them. As a concrete example, the arithmetic mean of 9 and 1 is 5. The geometric mean of 9 and 1 is 3, and 5 and 3 don't look anything alike. And before I get to the real beautiful theory about the arithmetic and geometric mean, perhaps the only theorem that is immediately accessible to school-age children about arithmetic and geometric means is the famous arithmetic geometric mean inequality. If A greater than or equal to B are positive real numbers, then their arithmetic mean is always at least as large as their geometric mean. I found this photograph on the internet proving this. So if you want to prove that the arithmetic means are never smaller than the geometric means, draw a square whose side length is A plus B, as fashioned here on the left. And if you're good with computers, color it in the way that you see here. And on the right, draw exactly the same square, except do not color in the little itty bitty square that you find in the middle. As a visual cue, this square is drawn so that A is a little bit bigger than B. And so you can calculate the area of the white stuff. The white stuff is the large square minus the 4 rectangles outside. And because we view A as being bigger than B, throwing what you get in A and what you get here is that A plus B squared minus A minus B squared is 4AB. And so we get that when you do the algebra, A plus B squared is at least 4AB, and immediately you get that the arithmetic mean is at least as large as the geometric mean by picture. But there's something much, much deeper about the arithmetic and geometric means, which I think makes a very important connection to special functions, and the first of the hypergeometric special functions. So given two positive numbers that are distinct, A greater than B, then the arithmetic geometric mean sequence is an intertwining sequence of order pairs, A1, B1, A2, B2, A3, B3, and so on and so forth. The first pair are the numbers you started with, A and B, and every subsequent pair is nothing more than the arithmetic means and the geometric mean of the preceding pair. And so in this way, you get an infinite sequence of real numbers. So if we begin with the 9, 1 that I started at the outset, again, the arithmetic and geometric means are 5 and 3. If you take their means, their arithmetic mean you can see is 4. What is harder to see is the geometric mean, which is the square root of their product, square root of 15, is 3.87 something or another, much uglier number. If you repeat this process, the arithmetic mean of those two numbers is 3.9364 ... And the geometric mean is startling if you've never seen this before. It's 3.9362. It's almost the same. And then when you take their geometric mean, you now need to have a good calculator to distinguish that these aren't the same number. They're very, very close. This arithmetic mean is definitely larger than the geometric mean, but to actually locate where the difference occurs in the decimal expansion takes a calculator or Ramanujan. And so this is what's very beautiful about the arithmetic and geometric means. It's a device that people use in approximating with incredible speed various kinds of expressions. Perhaps the most famous AGM expression that takes advantage of this rapidly convergent intertwining set of ordered pairs is this beautiful formula of pi, assembled by Euler in the 18th century. Imagine carrying out the arithmetic and geometric mean process with the two positive real numbers square root of 2 and 1. So I will always make A the bigger one. And if I forget, I might as well, but it doesn't really matter because averages are commutative. I will now start adding a subscript boldface R to indicate that this is the process that we're doing over the real numbers. So it turns out that if you assemble the arithmetic and geometric mean sequence for square root of 2, 1, you get a sequence of numbers a n, b n. And with these numbers a n, b n, let's fashion real numbers called Pn, which are a of n squared divided by this very funny looking finite sum of quantities coming from these terms in the sequence a1, b1 up through a n, b n. And remember, because the AIs are strictly bigger than the BIs, these denominators never vanish. Although the AIs minus BIs are getting very, very close together, we're multiplying these by exploding powers of 2, and it's not difficult to show that this number Pn is actually also convergent itself. And what Euler showed is that as n goes to infinity, these real numbers converge to pi. Why do we like this? Well, to see that this is really beautiful, all we have to do is work out a couple of numerical examples. Using square root of 2 and 1 in this formula, you get P1, that's 4. Using the first two terms in this arithmetic geometric sequence, P2 is 3.1876 ... And then the third term is 3.14168. That's really nice. We got the approximation of pi accurate to 3 decimal places just by computing 3 terms of the sequence. How beautiful is that? Well, that might be beautiful, but this is extraordinary. If you then compute the 4th term in the sequence and then compute the 5th term in the sequence, you respectively get 11 and 20 decimal places of pi respectively. And that is just beautiful. If you've never seen that before, this is the kind of thing that you could show to students why special functions are truly amazing. Special functions are generally devices that can be used to take a theoretical solution into involving these special functions expressions that can be used to prove theorems, or in this case, compute digits of pi. And what is the main tool? What is the main emphasis? What is the main deep idea that is underlying this incredible rapid convergence to pi? It's this one integral. People who work in special functions love gamma functions. They love integrals. And one of the first famous integrals you will study is something like this called IAB. So again, I'm going to put a lowercase r, blackboard bold R, when we're thinking about real numbers. So if a greater than b are 2 positive real numbers, IAB we define to be this integral. It's an elliptic integral, the kind of thing that Gauss studied. Elementary calculus will show that if you change variables, if you replace a by the arithmetic mean a plus b over 2 and replace b by the geometric mean square root of ab, that you get the same number. How nice is that? So in this way, this very exotic sequence of real numbers that becomes very hard to compute numerically, They're all tied to a single integral evaluation that is fixed the moment you fixed your first pair AB. So you have this long infinite sequence of identities. And where does this formula for pi come from? The formula for pi comes from Euler's very clever manipulation of the following formula for Gauss, where Gauss was able to calculate this integral in terms of this modified 2f1 hypergeometric function. Just like I have the letter capital R to indicate the real numbers, later I will be talking about other kinds of hypergeometric functions. So this superscript, the word class, is meant to mean classical, or the classical Gauss hypergeometric function. Great. So a few months ago, I was wondering why I couldn't find any beautiful literature with regard to the arithmetic and geometric means over finite fields. For example, fix your favorite prime P and just try to emulate arithmetic and geometric means over finite fields. There are some obstacles, as I will describe, but there were obstacles already present in the real numbers. And I was unable to find anything I thought at all remotely satisfactory. So, so Neelam, Michael, and Waylun and I decided to work out what this theory would be. It's not difficult mathematics, so I don't want to make the mistake in having anyone think this is something like working on the Riemann hypothesis. No, 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 no. Instead, I think I'd like this talk to be a little adventure where all of you find beautiful mathematics just by taking on the viewpoint that it's a good idea to try to generalize people like Euler and Gauss. And that's what I want to do in the case of the finite fields. So although it might not seem necessary to do this, let me take a moment to analyze some of the things that were important when we defined the AGM of the real numbers. The first thing is that half of the real numbers have square roots. Let's not worry about how to exactly count. Let's just say half of the numbers are positive, half are negative. The negative numbers don't have real square roots, so half of the real numbers have square roots. How do you choose a square root? Well, by convention, since grade school, we were taught to choose square roots to virtually always be non-negative. But we all know the square root of 4 actually we have a choice, and the choice is either 2 or -2. And for many reasons, we just declare square roots to be positive. For us, this actually is a very important point, because if we had not defined the geometric means to be positive, then the next square roots would not exist, because only half of the real numbers have square roots. Square root of I is square root of -1. That would be complex. So it's very convenient that we've declared square roots to always be non-negative, because it allows us to seamlessly continue with our AGMs over the real numbers. And like I said, strictly speaking, these first two bullet points are required because the square root of -1 is not real, and we want to ignore that was a choice. So what are the analogs of these 3 points if we were to study a finite field FQ, like Z mod PZ, where P is a prime? Well, from first elementary principles, we know that there are Q minus 1/2 quadratic residues in a finite field FQ. So Q could be a prime power. We just don't count 0 to be a square. Just like we don't include 0 in the AGM, because the moment you have 0, the geometric means are nothing but 0. So just like half of the real numbers have square roots, half of the non-zero elements in a finite field also have square roots. So is that a problem? No, it's not a problem. It's exactly analogous to what we had before. Now, we don't know how to choose signs for square roots in finite fields. How do we actually do that, right? There's no notion of positive versus negative that's available to us in finite fields. So how would we define an AGM so that we were guaranteed to have a next geometric mean, right? If you take a pair AB, I need to know that the square root of AB exists. And finally, in the third point, does it matter whether or not -1 is a quadratic residue? That's something like the statement that square root of -1 isn't real. There are finite fields where -1 is a quadratic residue. Is that subject going to be different from the situation where -1 is not a quadratic residue? And so it turns out that if we consider finite fields FQ, where Q is 3 mod 4, all of these 3 items are exactly in correspondence with the three items we know from the real numbers, because if Q is 3 mod 4, then we know that -1 is not a quadratic residue. Everything I say actually does extend to finite fields FQ for all Q, but in this talk, I'm just going to focus on Qs that are 3 mod 4 because it is exactly in correspondence with our intuition from the real numbers. So the AGM that we want to define over finite fields FQ will look very familiar. Let A and B be units. FQ star means non-zero elements of FQ. Let A be elements of the finite field where A isn't plus or minus B. This just guarantees that the arithmetic and the geometric means don't degrade to something trivial. But I'm also going to require that their product is a perfect square. And that is not a requirement because we never talked about in the real case the arithmetic geometric mean of -7 and 3, because then their product would be negative. So this is exactly like choosing two positive real numbers, except for the finite field, I'm choosing two elements whose product is a square. And then we define the finite field AGM exactly using the rules that we used before. And because that, we know we have a choice. The square root of an minus 1 times bn minus 1, I have two choices. It's a square. So how do I choose the square root? Well, because Q is 3 mod 4, exactly one of those next products will itself be a square, whereas the other one will not, because -1 is not a quadratic residue. So I can choose the quantity bn minus 1 when I take these averages to guarantee that the AGM will go on, and I can do it in only exactly one way. So it's in this way that the AGM is very well defined when Q is 3 mod 4, because I had to make use of the fact that -1 is not a square. And that's, as I said, what guarantees that the AGM over the finite fields will exist seamlessly in exact analogy with the AGM we know for the real numbers. So my guess is that maybe none of you have done this kind of thing before. If you have, I'm very happy, but if none of you have done this before, let's take an example. Let's consider Z mod 7Z, the finite field F7. Let's choose A and B initial elements to be 1 and 2. I can do that because their product, 2, is a quadratic residue, right? I need to know that the square root, that the geometric mean will exist. So the arithmetic mean is easy. 1 plus 2 over 2 mod 7 is 5. How do I calculate the geometric mean? Well, 2 is the perfect square of two residue classes, plus or minus 3. Which one do I choose? Well, I have to choose between plus or minus 3 so that the next product, the next arithmetic mean times the geometric mean, is still a quadratic residue. So I'm either choosing 3, which would require that 15 be a residue, or I'm choosing -3 because -15 would be a residue, but it is not. 15 above 7 is 15 is a quadratic residue. So the only choice I could make is to choose B2 to B3. So in this way, the arithmetic and geometric mean over the finite field F7 begins with the pair 1, 2 that I started with, and we just worked out the next pair, 5, 3. And if you repeat these steps, 5, 3 will give you 4, 1. 4, 1 will give you 6, 5. 6, 5 will give you 2, 4. 2, 4 will give you 3, 6. And then 3, 6 will give you 1, 2 again. So one of the reasons why you may have never thought about the AGM over a finite field, or it's not popular, is because these aren't infinite sequences. Over a finite field, there are most finitely many ordered pairs. So no matter what, this sequence is going to have to return to some element it had seen before and will therefore enter an orbit. That's not a negative thing, because as someone who was curious, I wanted to know, what do these orbits look like? So just a moment's thought. What if I started with the AGM with 6, 3 right here? From what we just saw before, 3, 6 goes back to 1, 2. So I know that 6, 3 enters into the orbit that I calculated above. AGM starting with 6, 3 enters into this length 6 orbit that we calculated in the first example, right? And because means are commutative, you already know that whatever the last element is in an orbit, there's going to, you can reverse the order and enter into the orbit as if, because you already have that complete information. But the question is, what do all of the orbits look like? So let me have some fun. If you study the AGM over F7, computing all of the orbits like this, what you will discover is no matter what pair you start with, your AGM over the finite field F7 fits into this picture. The orbit that you see at the top consisting of these 6 nodes is nothing but this orbit, depending on where you happen to start. The 6 nodes in that bell head are these orbits in order. That's these guys. And what are these little 6 little yellow dots below? These 6 yellow dots before are nothing like the tag-ons of the 6 threes. For every element, if you reverse the pair, you can put it in front of the orbit you find, and you know that that will enter into this orbit, and that's what these little dots here down below are. So I call that a jellyfish. I try to draw this to resemble a 3D image of arithmetic and geometric means over F7, and you get this picture of 12 nodes. Out of the 49 possible nodes, 12 of them make up arithmetic geometric mean sequences over F7. If you carry out the same calculation with the finite field F19, so remember these Q's are prime powers that are 3 mod 4. Without putting labels and ordered pairs for each of the dots, if you do that, you'll find that the arithmetic and geometric means over the finite field F9 breaks up as 8 distinct mechanisms. These 6 jellyfish, each with 12 nodes, and 2 larger jellyfish with 36 nodes. There's an 18 orbit here. There's a disjoint 18 orbit here, each of those with a little tag-on tentacle leading up to it, just like I described a moment ago in F7. So is there a theorem that says that in terms of images like this, the AGMs must have a certain shape? There is. Before I state it explicitly, let me tell you what the parts of what the conclusion is. For every FQ, and again, for me, Q is always 3 mod 4, if you compile all of the AGM sequences for that finite field, what you will always get is a disjoint union of directed graphs. And I will denote that by JFQ, MathCal JFQ. And each of these other J's are jellyfish. They are like each of these individual disjoint gadgets. Every jellyfish will have a bell head, an orbit at the top. And that orbit will have the property that every node in the orbit has a length 1 tentacle dropping to it or leading to it. Nothing else could ever happen. So for fun, I call the collection of these directed graphs a jellyfish swarm because they have bell head orbits with tentacles. And you might ask, what is the general theorem about these AGMs? Well, here's the theorem. The following is true for every finite field FQ where Q is 3 mod 4. If you were to count the number of nodes across all of the jellyfish that you find, there's Q minus 1 times Q minus 3 over too many nodes. That's the number of nodes. That's the number of pairs that make up a swarm. As I mentioned before, every jellyfish, these are this distinct, disjoint, non-intersecting directed graphs. Every one of them has a bell head in orbit with a length 1 tentacle leading up to each of the nodes in the orbit. Nothing else is allowed to happen. And finally, using elementary number theory, give me a positive integer n. If there are any jellyfish with n nodes, and we've seen examples of 12 and 36. If there are any jellyfish with n nodes, how many of them are there? Well, I don't have a formula for it, but I know if I count the number of jellyfish with n nodes, then that number times n is always a multiple of q minus 1. All right, so this is the kind of stuff that follows very quickly from a course in elementary number theory. You need to know a little bit about a group action on the nodes. You need to know a little bit about quadratic residues, and a little bit of a combinatorial argument to see that the jellyfish are the shapes of the distinct graphs. So let me not sketch out that proof, because this is just the beginning of a very beautiful story that I want to tell you. So you might ask, if we were to consider arbitrarily chosen finite fields, what do these swarms look like? Do they obey some general rule as Q grows? Because after all, the parts of this theorem is the stuff of elementary number theory. Maybe this is all the stuff of elementary number theory. And the point I want to make is that no, this is definitely not just the stuff of elementary number theory. Immediately after these three facts that make this theorem, you descend into very difficult questions. So one of the questions you could ask is, what are the typical sizes of these jellyfish? If I gave you an element in the AGM, when do you expect that AGM to come full circle and return to some element you've seen before? As a function of Q, the order of the field, are there natural expectations? Well, over the finite field F67, if you do the calculations, you'll find that there are jellyfish with only 18 nodes. Let me remind you, every jellyfish has a bell head with tentacles below them. So an 18-node jellyfish really means that there's an orbit of length 9. They're pairs AB, and when you go to the AGM on the 9th term, you got back to where you started. Or after 9th term, you get back to where you started. The very 10th term is the initial entry point. And if you think about it, over F67, that doesn't seem very long. Take another prime, F83. The finite field F83 is not a whole lot bigger than F67. But in this finite field, there are jellyfish with 410 nodes. That means that there is an orbit of length 205. And think about that. If you were to do that calculation by hand, you might doubt your calculations. You know that the AGM has to eventually return to some numbers it's seen before. But after your 204th iteration, you're probably wondering, I wonder if I made a mistake. I'm running out of possibilities. It takes 205 steps for some pairs to come back and complete cycle. So what explains this chaotic distribution of these sizes? That's a good question. So I don't want to mislead you by cherry picking some of the primes. So here's a complete list of the number of jellyfish that you find for all of the Q's starting at 3, going up to 283. Okay. So I hear someone's microphone. So if you could, yeah, it's causing a feedback. So if you could mute yourself. Yeah. So over the finite field FQ, when Q is 3, there are no jellyfish, none. For the finite field 283, yeah, so whoever's microphone is causing that feedback, please mute yourself, because here in the United States it's causing terrible feedback. So for the finite field F283, there are 35 jellyfish. So the comments I want to make are as following. Look at these consecutive primes. Look at 191 and 199. There are only 14 directed graphs in that AGM, but for the very next prime, there are 101. What is it about 199 that means that the AGMs are all really, really small, but over the finite field 191, there are these long orbits before the AGM returns to something it's seen before? Or here, 211 and 223, they're adjacent primes, but for 211, there's 120 directed graphs in the AGM, but for 223, there's only 18. And this continues. So beyond this table, for the finite field 479, there's 18 AGM jellyfish. But for the next prime, 487, there are 359. What is it about the prime 387 that says if you pick a pair at random, AB, the AGM is going to be a little itty bitty orbit? These are deep questions. All right. So what I've described to you are questions that can be understood if we rewrite them and transport them into a little bit of number theory. So now you know where the jellyfish comes from. It's just my fun way of envisioning the AGM sequence. So if I gave you a finite field I have a collection of jellyfish, as I've described. These are the AGM orbits with the tentacles that lead up. That just comes from commutativity. And every one of the nodes, and remember, every one of these nodes is an ordered pair in an AGM. Every one of these nodes, I'm going to map to an elliptic curve, depending on the numbers that make up that pair. And I'm going to study the collection of elliptic curves we get here. And you'll soon see that this is a very special device in special functions. Great. So the takeaway is that if we study AGMs over finite fields, I want to view it as a device for organizing elliptic curves by means of averaging. So what are the elliptic curves? Just for us, they're equations of the form y squared equals a cubic polynomial in x, where the discriminant of the cubic is non-zero. It doesn't have repeated roots. And in number theory, we're very interested in a theorem that classifies the rational points, the points x, y, where they're both rational numbers, on the curve. And this famous theorem of Mordell says that the rational points, so although there's infinitely many points here depicted in red because it's a curve defined over the real numbers, when you restrict to only include points where both coordinates are rational, the curve, the set of points takes on a group structure. And as a group, it is a finitely generated abelian group, which means there's finitely many points, the torsion points, perhaps in direct copy with but finite number of copies of z's as a group. And although this is not the point of this talk, let me just highlight, computing these groups is one of the fundamental open questions in number theory. Is there an algorithm for computing these groups in the set of rational points? Yes, but it's not proven to work in every case. It's called the Birchon-Swinnerton-Dyer conjecture. Why do we care about them? Well, we care about elliptic curves because they encode a lot of beautiful number theory problems. For example, here is a right triangle with some complicated side lengths with area 2006. Whether or not an integer is an area of a right triangle with rational number side lengths is equivalent to whether or not there's an elliptic curve that has points of this shape. So if you replace 2006 by any positive integer n, whether or not there are rational points on that equation boils down to whether or not is equivalent to asking whether or not there are any rational points on this curve. Ramanujan's taxicab number, appropriate for today, is the statement that 1729 is the smallest positive integer that is the sum of two positive cubes in two different ways. And if you translate the sum of two cubes in two ways, you realize that you're studying points on this elliptic curve. So if you want to study integers that are sums of cubes, n, you'd put n here. Y squared equals x cubed minus 432 n squared. So there are lots of problems that we know can be translated into elliptic curves. So what does this have to do with finite fields in the AGM? Well, I think many of you know the connection between the Legendre's hypergeometric functions and Gauss's 2f1s. And what we want to do is we want to explain how that works all over a finite field. So for every element in a finite field lambda other than 0 and 1, I want to write down the elliptic curve as a function of lambda given here. Lambda appears right here. And requiring that lambda isn't 0 or 1 is just the rule that there are no repeated roots on the right-hand side. Just from elementary number theory, if you haven't seen this before, never mind, this is an elementary calculation. These curves over finite fields always have a subgroup of points, Z2 cross Z2. Klein's Z2 cross Z2 group is always a subset of the points that satisfy this equation. Moreover, as an abstract group, the set of points on this curve where lambda is now a perfect square is also a group. And it is a finite group because only finitely many ordered pairs x and y over a finite field. And you can show that the 2-CELO subgroup, the maximal subgroup that is the 2-power order, has this very special shape. It's Z2 cross Z2 to a power. This B could be 0, but the point is you can't have two parts. You can't have a rank 2 subgroup that has elements of order 4 in them. Only one part of them could have an element of order 4 in them. And when this lambda is a perfect square, there is always at least one point of order 4. So what I want to do with the AGM is as follows. For every finite field FQ, I'm going to define a map psi that takes ordered pairs AB and gives me the Legendre curve E lambda AB, where the lambda is B squared over A squared. So the lambda here is going to be B squared over A squared. If you have an element AB in the AGM, I'm just going to just put in B squared over A squared right here. And this is going to be keeping track of that entry in the AGM. And if you do that, if we go back to F7, the finite field F7, and look at the jellyfish, this was the whole jellyfish, an amazing thing happens. Although these ordered pairs are very different, under this map, they collapse to the same curve. 6,3 maps to the curve E2, and this whole orbit collapses just into multiple copies of E4 over and over and over again. If we did F19 and apply this map, so again, every one of these nodes is a pair of numbers, AB. I turn that pair into B squared over A squared, and I plug that into an equation. If I apply that rule to this 12-node jellyfish and flatten it out in terms of the elliptic curve, so this 6 is the B squared over A squared mod 19 becomes 6, I get this picture. So I'm going to do that to every one of the AGM orbits. And now take a look at it. What you see is there's remarkable structure. E6, 9, 16, 9, 16, 9, 16. It's a different kind of orbit. And then there are these tentacles, 6 into 9, 17 into 16, 6 into 9. None of these entries out here are different from those that you would expect based on the number theory. So as you now see these directed graphs coming from just arithmetic and geometric means become directed graphs on elliptic curves. So my question is, what do those graphs mean? And what is the significance of an arrow? Right? The arrow in arithmetic geometric means, here we knew, take arithmetic average and geometric average. That goes from here to here. Do it again, goes from here to here. Do it again, you go from here to here. What does it all mean now that I've got curves? And so is it the case that the arithmetic geometric mean from arithmetic over a finite field defines an exotic process on these elliptic curves for which there is additional structure allowing us to prove something that we couldn't have seen before just by averaging? And that is all true. So it turns out that when viewed as directed graphs of elliptic curves, the significance of the arrow is what's called an isogeny. Think of these as changes of variables. They're not quite homomorphisms. Homomorphisms can be are examples of isogenies. So given two elliptic curves E1 and E2, a non-constant morphism, these are rational maps in the variables, is called an isogeny if it respects the identity and has finite kernel. You don't need to really know what those words mean because the general theorem is what's on this slide, and it's all explicit in terms of equations. So if you have a finite field, FQ, where Q is 3 mod 4, then for every perfect square, each Legendre form curve where the parameter is a perfect square is in the image of the AGM. And in particular, I know how many times it will occur in this network of curves, Q minus 1 times. What is the significance of the arithmetic and geometric mean rule? So AN plus 1 is the arithmetic mean of AN and BN. BN plus 1 is the geometric mean of AN and BN. What is the significance of that rule? Well, the significance of that rule is that if you write down the elliptic curve for AN, BN, and write down the elliptic curve for AN plus 1, BN plus 1, again, that's just B squared over A squared in that last parameter, then what the arithmetic and geometric mean sequence is in disguise is this isogeny. every point on this curve maps to a point on this curve by this rule. And the arithmetic and geometric mean rules make this happen. Great. And if you calculate the kernel, 0, 0 is on every one of these Legendre normal form curves. In particular, it's in the kernel, and you can show nothing else is in the kernel. Great. So the sophisticated structure of AGM becomes an exotic structure on elliptic curves over finite fields. Which elliptic curves is it parameterizing? It's parameterizing the Legendre normal forms curves where the parameter is of any arbitrary perfect square. So what do the jellyfish represent? What ties them all together? So let me remind you that the notation DFQ counts the number of jellyfish. Over F7, there was only one of them. Over F19, there were 6 of them. And then later I showed you this table with this oscillating crazy behavior for how many jellyfish arise in the AGM. So what is true about each individual jellyfish? Well, group theoretically and about elliptic curves, an amazing thing happens. There is an abelian group G such that for every pair in the jellyfish, it turns out that every one of the corresponding elliptic curves for these pairs over FQ have exactly the same group, right? The set of points on a curve over a finite field form a group. What ties them all together is that the group is the same. And the 2 CELO subgroup therefore must be fixed. You can count how many points are on the curve. The number of points on this curve is the number of points in this group. In number theory, it's customary to write this as Q plus 1 minus an error term called the trace of Frobenius. And so counting the number of elements in this group boils down to computing this number called the trace of Frobenius. And this is where we get back to special functions. Rather magically, calculating the number of points on these curves is computing a Gauss hypergeometric function when defined over a finite field in the parameter b squared over a squared. This was exactly the rule that you had to use if you were Euler, if you wanted to calculate pi. Why is it that the procedure for calculating pi rears itself up here in a finite field situation, again by AGM? So let me explain. First, an example over F19. Here are the eight jellyfish. Let's home in on one of them. Let's map each of those pairs to curves. Although these are different curves, when you compute the group structures of the points on these curves mod 19, they are all Z2 cross Z12. They are all the same group, Z mod 2Z cross Z mod 12Z. So let's return to the question, how many jellyfish make up a swarm? These were the crazy numbers. Adjacent primes could have as few as 18 and 387 jellyfish. We prove a theorem. For arbitrary epsilon positive, if Q is sufficiently large in 3 mod 4, then the number of jellyfish grows at least like 1/2 times the square root of Q. Why is that true? Thanks to our examination of these things as elliptic curves, I know that the number of jellyfish is at least as large as a number of different groups of points that you get when you study the curves E lambda squared. That's a lower bound. And you can just, for all of the possible values that correspond to the traces of Frobenius, you can construct at least one group for all of those possible values. And if you just count the number of elements S in this interval that satisfy this congruence condition, you get 1/2 root Q. So for every integer that satisfies a congruence shown here, I know how to write down a group that actually arises as the group of points. And therefore, the number of distinct jellyfish, and they have to at least be as large as the number of groups that come up, is at least this large. How close is this lower bound to the truth? It's actually very close. So here are some finite fields. Here are the number of jellyfish that you get. And if you compare those numbers with 1/2 square root of q, you get these numbers. And notice that for the finite field F7703, there are 87 jellyfish, but my first attempt at a lower bound predicts at least 43.8. So what is the true order of magnitude? I think if you work harder with our argument, the lower bound you could probably show, I have a PhD student working on this, will probably show is like square root of q log q, which would be essentially these numbers almost on the nose. So my first argument about turning this into a problem of counting groups is, I think, almost assuredly the right answer. You just have to work a little bit harder than getting one group for each possible size, because there are occasional choices where there'll be more than one possible group. Depends on the factorizations of these numbers. So what types of curves are in these jellyfish? Why is it that the Legendre parameters 6, 9, and 16 appear here? What can we say about the number of different curves that are made up? Well, something like counting spots. Think of E6 as green. So here's green, here is green, here is green. Think of E9 as blue. So here is blue, here's blue. You can think of the AGM as giving rise to spotted jellyfish of different colors. How many colors are there? So this is where Gauss appears again. Gauss's hypergeometric functions, when reinterpreted in terms of quadratic finite fields, appears in the AGM. And a different work of Gauss appears here in terms of counting the spots. If you didn't care about the exact parameters, let's just count the different kinds of E's that you get. So here's 6, here's 9, here's 16, and 17. There are 4 different kinds of spots that make up this AGM. Well, Gauss was famous for his work on class numbers of binary quadratic forms. The discriminant of this binary quadratic form is b squared minus 4ac. If it's positive definite, it only represents positive integers when the leading coefficients is non-negative. So we will restrict to that case. And as well known, SL2Z acts on this set of fixed discriminant quadratic forms by this action. And this action preserves the discriminant. And one of the most important contributions of Gauss to algebraic number theory is the realization that the number of orbits of the SL2Z action on fixed discriminant quadratic forms is finite, the so-called class number. So although there's infinitely many discriminant minus D positive definite binary quadratic forms, up to SL2Z change of variables, there's only finitely many of them, and their total number is what we call the class number. He also showed that these orbits of forms form groups, the abelian groups called ideal class groups. For discriminants -4 and -84, you can work them out. There's only one orbit for discriminant -4. For -84, there's 4 of them. These ordered triples are the coefficients ABC. What does this have to do with AGM? It has everything to do with AGM. So let Q again be as it has been throughout, and let MFQ of S be the number of distinct isomorphism classes of jellyfish. So a J invariant is an isomorphism class invariant for elliptic curves, where the AQ of I is fixed to be S. This was the hypergeometric function value. It's a count. And this is going to be the trace S jellyfish spot count. And what is our theorem? Our theorem is that if the number of curves in the jellyfish with this S is non-zero, then how many of them are there? It's a class number. It's a modified Gauss class number that's called the Hurwitz-Kronecker class number. So the class numbers that we study, the same ones that appear all over number theory, appear in AGM if you want to count the number of spots, the different types of elliptic curves that appear. So here's an example. Over F19, there were 2 families with trace 4. They both give rise to this collection of 4 orbits. And so when you add them up and plug in the 4 and the 19 here, you get a class number of 2, which is the fact that these 4 elliptic curves only give rise to 2 distinct J invariants. Although you see 4 elliptic curves, E7 and E11 are isomorphic. E4 and E5 look different, but they are isomorphic. So these 4 collapse down to 2 different curves up to isomorphism, which is indicated by the fact that Gauss's class number is 2. What I'm telling you is you can compute class numbers by going through AGM and then counting spots, as I've done here in this example. So to now very quickly wrap up, what does all of this have to do with special functions? I began with pi in the AGM, and I very, very briefly snuck in the 2f1 into one of my slides a moment ago. The answer to this question is it has everything to do with AGM. So going back to what I started with, the AGM over the real numbers is all about the rigidity of this elliptic integral, IAB. As I mentioned before, under change of variables involving the arithmetic and the geometric mean, the elliptic integral is fixed. The parameters have moved, but the actual value is fixed. So as you make your way through the arithmetic and geometric sequence, you get an infinite sequence of exact evaluations that are all identical. But Gauss famously made use of this change of variables to come up with a very rapid evaluation and approximation for pi. How does that arise? It arises from the hypergeometric evaluation of this integral, right? Special functions often begin with the study of the gamma function, the beta function, and their connections to 2f1 functions. And here it is. What does it have to do? So the AGM is this identity. I'd like to say the AGM is this identity combined with rapid convergence, combined with the combinatorial properties embodied in the hypergeometric function. What about the AGM over finite fields and elliptic curves? Well, what could you replace this integral by? Oops. What could you replace this integral by? Well, this is a square root. Over finite fields, we study quadratic residues. So over a finite field, you can replace that integral by the sum over x of the product of these quadratic residue symbols. Phi q is your Legendre symbol, but I didn't want to have too many parentheses. So this is the Legendre symbol, x above q, x minus 1 above q, and this more complicated thing above q. But look, that's x times x minus 1 times x minus 1 minus b squared over a squared, exactly as we have here. If there was a finite field analog of this integral, I claim it must be this. By the way, you can show, and John Green did this in a beautiful PhD thesis in the 1980s, he was able to show that if you had arbitrary characters like Legendre symbols over finite fields, that a 2f1 in those parameters would be rewritten as a sum over the finite field, these products. What does the bar mean? It means complex conjugation. Legendre symbols are just real numbers, so complex conjugation does nothing. And so in particular, this finite sum becomes this finite field hypergeometric function. And look at that. Doesn't that almost look exactly like Gauss's formula for his integral? Indeed it does, because if you compare, all the parameters make sense. Change the field of the real numbers to the finite field. Keep the same symbols A, B. View pi as Q. The volume of a finite field is its order, it's Q. The volume of a circle, a radius 1, is pi. All of these analogies work. Replace the numbers 1/2, 1/2 by the characters that have order 2, the Legendre symbol. Replace the number 1 by the trivial character, the one that takes the value 1 everywhere. And if you make those identifications, this finite field sum is analogous to this real number integral. And then all of the accidents that Gauss took advantage of to prove his formula for pi, I realized together with my collaborators, Saikia, Griffin, and Wei Lun, and recognized that this is all the AGM in disguise over finite fields. And when you do that, you discover that it organizes elliptic curves. So to summarize, what does AGM over and jellyfish and elliptic curves have to do with special functions? They can be thought of as the analog of Gauss's and Euler's theory, but written down over a finite field. Here is the picture, and I hope you find this very interesting. If you generalize Gauss, his two F1s to finite fields and the beautiful theory of the AGM, you get an equally beautiful theory involving elliptic curves where the theorems, instead of being infinite rapidly convergent sequences, is about a taxonomical device in number theory. That infinite sequence turns into orbits, which turn into these jellyfish swarms. And what we've actually done is we've organized elliptic curves. So the takeaway, I hope you agree that starting with average and square root, you get something elegant. And this elegant thing has structure. And this structure is all about what two F1s mean over finite fields when you take the time to figure out what they might mean. Difficult problems remain. As I've shown you, it's not elementary stuff, just like rapid convergence of pi is not elementary, and the work is ongoing in those directions. Super. And with that, let me conclude. Are there any questions?
Please ask if you have any questions. If there are no questions, thank you very much, Professor Ono, for the excellent lecture.
Okay. All right. I hope you find it very beautiful. It's just taking average A plus B over 2 and square root of AB over a finite field. And if this is a subject you find very beautiful, this is only the first step. Professor, imagine.
Professor,
yes.
Can I have a quick question?
Okay.
You have applied this jellyfish swarm connection with elliptic curves. Did you apply this to any other areas? Means, have you taken this jellyfish swarm instead of that? And there is a connection with the graph theory also, I presume.
Oh yeah. Yes. Now this I've only written one little paper on this, and that's what's in this. Yeah, there's a lot of, yeah, I'm almost certain that graph theorists will start counting these, right? What is the smallest AGM graph that you get over FQ? What is the largest one? How many of them are there of each? And people start doing spectral questions on this, I'm sure. It's so easy to compute on a computer and get zillions of examples and see very exotic behavior that maybe no one's ever found before. Maybe we really are the first people to do these calculations.
One more question that you encountered with the classical hypergeometric function 2f1. Did you encounter any other special functions like any other hypergeometric functions or?
Along this kind of work? Absolutely. So maybe many of you are fans of the Clausen's 3f2 expression relating 3f2 and a square of a 2f1. If you write that down in a finite field, that has a very deep meaning. Very, very deep meaning in geometry. I've made use of that maybe in 5 or 6 different papers in my career, going back to the 1990s.
Thank you, Professor.
Yeah, so I didn't start this finite field business. John Green, who is a PhD student of Dennis Stanton, wrote his thesis on this, and you'll discover that people like Ron Evans, who was one of Bruce Byrne's earliest PhD students, has written quite a bit on this. Dermot McCarthy has written quite a bit on this in his thesis. In the United States, there are people writing theses on this at MIT, University of Minnesota, Texas A&M, some other places. So although it doesn't have this long history like the classical theory of special functions, this is a subject that is growing very rapidly. If you're expert on special functions, I invite you to join the area. If you love the gamma function, the first question you could ask, in what way is the Gauss sum the analog of the gamma function? And you'll discover almost every beautiful property of the gamma function has an analog in finite fields, right? And there's much work to be done there. This is why I wanted to share this with you, right?
Yeah, it is really motivating, and in fact, many students can work on this area, further extend these results which you have told. Even in in
Absolutely.
abstract algebra and algebra, who are working in algebra has a good chance to interact with the special functions as well as.
Right. So if you had a parameter AB and computed the finite field function 2f1 at 1 minus b squared over a squared, there's a group there, right? Because that group is counting the number of points on the elliptic curve that corresponds to, right? What's the law? The special function will give you a number, but how do you know then which group has that order, right? So that is exactly the question I did not answer. For every one of the values that comes up, I constructed at least one group. But in some cases, there's more than one group that have the same order, right? Groups of order 8, right? Z2 cross Z4 or Z8. That cannot happen for these elliptic curves, but there are many orders where there are multiple groups that could arise that correspond to the different jellyfish. And answering that is exactly the problem of counting how many jellyfish come up. So there's two parts. How many special values? You have to become an expert on the 2f1s. What are its values? What can it give and what can it not give? And for the values it gives, how many groups are allowed to correspond to that value? Is there an upper bound for the number of groups that could correspond to a specific value? All of these questions you could begin to ask. And we haven't done that. But yeah, all of these are very, very tractable problems. I invite you to invite Neelam Sakia when she returns to India later this year after her postdoc is finished, because she will be one of the local experts on this subject. Rupam Barman and Gautam from IIT Guwahati also have thought a little bit about this. So please don't view that as another area of number theory. If you work in special functions, you're doing the same thing, with just for the moment with different goals.
Professor Bhargava, did you want to conclude? Or
Yes, thank you very much, Professor Vana, for the excellent lecture. And I hope we'll have a lot of followers in India once the student comes back.
Thank you.
Thank you very much.
So thank you, Professor Ken Ono, for your wonderful and insightful lecture, and Professor Bhargava for sharing the session. In fact, I have not mentioned anything about the R.P. Agarwal, who on his memory, we are celebrating this memorial lecture. Every year, starting from 2011, we are having this lecture. The first lecture was done by George Andrews, the second by H.L. Manocha, third by A. Mathai, fourth by in 2015 by Singeru Kanimestu, and fifth in 2016 by Michelle Waldsmith, 17 by Tom Kurwinder, 18th by S. Bhargava, and 19th by Claude Lewis. And in 2020 we had Professor Bruce Byrne delivered this R.P. Agarwal lecture, and in 2021 we are fortunate that Professor Ken Ono has delivered this R.P. Agarwal lecture. So on behalf of all the participants as well as from the Department of Mathematics, I extend our sincere gratitude to Professor Ken Ono and Professor Bhargava for this excellent session. So thank you, Professor.
All right, thank you very much, and enjoy and celebrate the day. In 10 minutes, I'm giving a lecture at Shastra from my basement. All right. Good day, everyone.
Thank you. Thank you. So thank you, Professor Bhargava.
Thank you very much. Thank you very much. So far, for your excellent organization.
Dear participants, we are coming to the end of the day one. We will be coming back on day two on tomorrow at 10 o'clock for the session 6. Please note that it is at tomorrow at 10 a.m. 10:05 is the timing is given in the schedule. So we will be go according to that plan. And Professor Ajay Shukla will chair the session, the first session, in which Professor Atul Dikshit and Subuhi Khan will talk. So thank you very much for your patient listening and for attending these sessions. Thank you. Is recording.